we want to give a characterization of an ideal, say Q, being P primary. So we discussed this lemma, which we will use again and again. So you fix a ring R, and there are two ideals, say Q and P, such that Q lies within P, which in turn lies within radical of Q. And number two is that if A times P lies in Q, this implies that A lies in P or B lies in Q. So if these two conditions hold, then P is a prime ideal, P is a prime ideal, and Q is P primary. So this is important characterization of an ideal. So let us prove this. Now first thing to notice is that we immediately have Q is primary. Now that is precisely because, if AB lies in Q, A lies in P, so A lies in P means that A will have to lie within radical of Q. So that is some power of A lies within Q or B lies in Q, and that is precisely the definition of Q being primary. So this just follows from this number 2 statement, because P lies within radical of Q. So the only thing we need to show is that there is equality here. P is precisely radical of Q, that is P is the underlying prime ideal for Q. So P is radical of Q. So for this equality, what we are going to do is we are going to start with some A in radical of Q and end up showing that this A actually lies in P. So you start with A in radical of Q, that means A to some power n lies in Q for some n a natural number which is non-zero. Now you pick n to be the smallest. So case 1 is, say n is just 1. So if n is just 1, then A would lie in Q, because A to the n is in Q and n is 1, and Q we are given lies within P. So we start with A in radical of Q, and that implies A lies within P. Second case is that if n is greater than 1, these are the only two cases, then you can write A to the n as A times A to the n minus 1. So notice this n is the smallest. So n is the smallest. Therefore this A to the n lies within Q, which we are copying from here. But A to the n minus 1 does not lie in Q because n is the smallest. So we have A to the n minus 1 does not lie in Q. Now that would imply that A lies in P precisely because of 2. So instead of A times P, we have A times A to the n minus 1. And so therefore if A n minus 1, so one of them has to hold. Either this portion has to hold or this portion has to hold. So we are saying that this B we are writing as A to the n minus 1. This is not Q. So it has to be the case the first one holds. So that is A is in P, as in 2. So you're just setting B as this element here, A to the n minus 1, and using this statement which gives you A is in P. And that's what we wanted to show. We start with A in radical of Q. For n equals to 1, it will lie within P, and n is greater than 1, again it will lie within P. And therefore there is a equality here. Every element lying here would lie here as well. So now we will summarize this in a remark and move on to decomposition. In this lecture we want to talk about primary decomposition. So before we do that, let us make an important remark. So let this Q be P primary. So this means if A times B lies within our this primary ideal Q, which is P primary, then either A lies within P or B lies within Q, or both of them can happen. So again, AB lies in Q. This would imply either A lies within P because Q is P primary, or B lies within Q. So this is the definition we are going to use whenever we want to prove some ideal Q is P primary. Now recall that this Q is a primary ideal and radical of Q is precisely this P right here. So that is what Q being P primary means. Radical of Q is P and Q is primary. So first proposition we want to do in this lecture is this: a finite intersection of primary ideals is primary. So we want to show a finite intersection of primary ideals is primary. So let Qi be a P primary, and this is a Qi as a primary ideal. It is P primary for all I, and say Q is Q1 intersection Q2 all the way to intersection Qn. So this Q is our finite intersection of primary ideals, and we want to show that this Q is primary because we want to show a finite intersection of primary ideals is primary. So to show is that this Q is primary. So first thing is that this is general result for any ideals. You take radical on both sides, the radical will go inside like this. So radical of Q is just radical of Q1 intersection radical of Q2 all the way intersection radical of Qn. So that will be, this implies this is from a general property of ideals. So any intersection of ideals like this, you can always take radicals and the equality will hold. Now each of these Qi is P primary. So Q is a primary ideal, that is each Qi is a primary ideal, and radical of Q is P. So for each of these radical of Q1 is P because each Qi is P primary. So we are just copying this statement here. So this is P, second is P all the way, this is also P, their intersection would also be P. So we have radical of Q is P. So we have to show that this Q is a primary ideal. That's what we want to show. So one of the things to show is the radical of Q is P. So this we have just shown. But we also have to satisfy this definition now. So we have to show that if AB lies in Q, either A lies within P or B lies within Q, and then Q will be P primary. You have anyway shown that radical of Q is P. So for this definition, let us copy this. So start with AB in Q, and we are saying B is not in Q. So either this has to hold or this has to hold. If B is not in Q, we will end up showing that A is in P. If AB is in Q, B not in Q, we'll end up showing that A is within P, and that will be the end of the proof. That will show that Q is P primary. And that's what we wanted to show, because you set Q as intersection of finite number of primary ideals. So we say AB is in Q. So then we have AB is in some Qi, because Q is intersection of all these Qi. So AB has to lie within some Qi. So AB lies within some Qi, but B we are saying is not in Q. So B does not lie in that particular Qi. So we are able to find a Qi which satisfies these two conditions. That is, B does not lie in Qi, but AB lies within Qi. So because Q is intersection. So for some I we have this same condition right here. But Qi is P primary. So this definition here also applies for this our Qi, which is P primary. But if Qi is P primary, then either A is in P or B is in Q, or in our case Qi. So we are saying B is not in Qi, so it has to be the case that A is within P, because this Qi is P primary. So since Qi is P primary, we have A lies within P using this, because we are forcing B not to be in Qi. And that's the end of the story. So we wanted to show this A lies within P. Let us now come to primary decomposition. So definition: the primary decomposition of an ideal I is a finite set of primary ideals Q1, Q2, Q3 all the way to Qr, such that you can write our ideal I as intersection of these primary ideals. So Q1 intersection Q2 all the way to Qr. So this is the primary decomposition. Each of these ideals here is primary. Now this decomposition is called minimal if these underlying prime ideals corresponding to each of these radical ideals are all distinct. So you say Pi, which is radical of Qi, these are all distinct. And number two is that you cannot just drop any Qi out. So you do not have any irredundant Qi. So no Qi can be omitted. In other words, if you take intersection of some Qi's where I is not in K, then this intersection is not contained within some Qk. So you cannot just drop some K out from our particular this decomposition. So we can start from any primary decomposition and replace some ideals which might be repeating or have the same radical by a single primary ideal. So if there are two radicals which have the same underlying prime ideal, you can replace those two with a single one of them which has the same prime ideal as the underlying their radical, and this will give us the minimal primary decomposition. So important remark is that this minimal primary decompositions is not unique. So these minimal primary decomposition of ideals are not unique. So say we have now two decompositions of x square comma xy. So one you can write as x intersection x square comma xy comma y square. This is nothing but square of our ideal xy square, and this is also equal to x intersection x square y. So you can see there are two minimal decompositions. So there are two minimal decompositions corresponding to this ideal right here. To a single ideal you have associated two minimal decompositions. So let us do some examples. So in integers, so say an ideal is given like this, just product of prime numbers. So some number, and we have just decomposed it into its product of prime numbers and corresponding powers, where each pi is prime. Now this ideal A has primary decomposition of this form: p1 n1 intersection p2 n2 all the way to pr nr. So this is standard primary decomposition. Now this primary decomposition is also used in algebraic geometry. So say you have kv is the coordinate ring of some variety v, and say ideal I lies within kv. So then you can consider a primary decomposition of this ideal. So say the decomposition is q1 intersection q2 all the way to qn. Each of these are primary ideals, and you take the radical of this, you get some prime ideal pi. So when you write it in terms of vanishing set, so you know this vanishing set becomes v of q1 union v of q2 all the way to v of qn, and then when you take the radicals you can have this equality here after taking radicals. So this will be equal to vanishing set of p1 union all the way to vanishing set of pn. So the idea is that once you these are all irreducible components, so we are basically taking an ideal I, you can decompose it, and then you can get to the irreducible components. But when you get to the irreducible components, you forget the multiplicities here because you're taking radicals. So what primary decomposition does is, this primary decomposition is in the purest form, in the sense it remembers the multiplicities. So it will keep track of multiplicities. So you have x minus a1 n1 all the way to xr minus ar nr. So you can decompose this primary ideal like this. But if you take its radical, then you lose these powers. You take the radicals, you can get irreducible components, but you lose these power. So primary decomposition keeps track of the multiplicity, it keeps track of these values n1, n2 and so on, because once you take the radical, these will just go away.